Okay, it's 1 minute past. All of you are late. Um, I'm kidding. I'm always late too. Okay, it is my pleasure today to introduce Emma Beasor. Emma is a faculty candidate. She is coming to us from the distant land of Arizona, where she is a Bart J. Bach Fellow. Previously, she was a Hubble Fellow, also at the University of Arizona, and before that, she did her PhD at Liverpool, John Moore University. See, there was a Moore. It was just not in the wrong,
Yeah, there is
the right place. Emma is an expert in the fates of massive stars, in particular connecting them to their supernova and compact descendants, which has huge implications for galaxy formation and also for gravitational wave sources. So I'm very excited to hear about massive stars today. Everyone, please welcome Emma.
Okay, is the microphone on? Can everyone hear me okay? Perfect. All right, yeah, so thank you for the introduction. I'm very pleased to be here. It's actually my very first time in Colorado, and my first time in Boulder. It's very beautiful. I'm having a lovely time. I'm going to be talking today about how to connect massive stars to their supernovae and their compact remnants. And Erica kind of already did this for me, explaining why massive stars are important, but I'm going to make sure you really know. First of all, they end their lives with an explosion, which is super cool. Beyond that, they are the direct progenitors to neutron stars, black holes, everything that is producing the gravitational wave signals that are detected by LIGO, Virgo, Cagra. They have a huge influence on their local environments, in particular stellar clusters, and they really shape galaxy and drive galaxy evolution, including many fundamental observables, such as the mass-metallicity relation. And finally, their explosions are factories for the nucleosynthesis of heavy elements. So I'll just show this periodic table. Everything that has a green color comes directly from the explosions of a massive star, and everything that has like an orange color on it comes from the death of the merging of neutron stars, which, as I just said, also come from massive stars. They have a huge effect on our universe. Why study massive stars now is another good question. This is actually a really exciting time to be doing this type of work. For one, there are numerous surveys online and coming online that are really exciting and that are giving us an infinite amount of data that we just haven't had before. So in next year, we should have data from Rubin-LSST. We also already have the ZTF survey, which is detecting supernova already. There's also LIGO Virgo, detecting gravitational wave sources. So we can really see what the endpoints of these stars look like and try and connect that to stellar evolution. And in addition, there are now evolutionary codes that are available for anyone to use. So for a long time, if you were a stellar astronomer and you needed to look at a model, you just were at the whim of whatever groups were publishing, whatever assumptions they made in their stellar models. But now we can go and we can fiddle about with our own models, make our own changes, and run them as we need them. But all of this new information is actually revealing a lot of tension between theory and observation. And I'm going to address a couple of these tensions in my talk. And what I hope that you take away from this is that all of these theoretical predictions are actually very sensitive to the assumptions that we're making during stellar evolution. And since stellar astrophysics does underpin almost all areas of astrophysics, it's really important that we do get these details right and we do understand the lives of these stars. Okay. So I'm going to go through the big picture, and this is a very brief, basic overview of what we expect massive stars to do. So a massive star is anything with an initial mass over about 8 solar masses. Between 8 to 30 solar masses, we expect stars to die as hydrogen-rich supernovae. That means they've held onto their stellar envelopes, and they should leave behind a neutron star. Above 30 solar masses, the canonical wisdom is that they should die as a hydrogen-poor supernovae and leave behind a black hole. So the hydrogen-poor supernovae means they've lost all of their envelope at the point of explosion. But in fact, binaries make this a lot more complicated. For a long time, it was assumed that massive stars were just single stars just going about their lives on their own. But in reality, most massive stars have a companion. So on this figure, the top curve shows the number of stars, the fraction of stars that have at least one companion. So for stars above 10 solar masses, so in this massive star range, you can see that it's almost 100%. And the fraction of stars that have multiple companions is also pretty high. But it's been determined that maybe 70% of massive stars are in binaries that will interact some way, whether that be merging, stripping, accreting. So this is actually a huge effect in the evolution of massive stars. But if we go back to the single star picture for a minute, this is what it kind of looks like. So for most of their lives, a massive star will burn hydrogen in its core and have an envelope. At some point, the core will be depleted of hydrogen. And at this point, you have a helium-burning core surrounded by a hydrogen-burning shell. At this point, the star will expand, and you will have a red supergiant star. This is what it looks like on an HR diagram. I'm a stellar astronomer, so I have to show multiple HR diagrams. And this is what it looks like. So the massive stars are on the main sequence, and they travel at pretty much a constant luminosity until they land in the red supergiant phase. And this is probably the last phase that these stars will live through before they die. It's a super quick phase. It's only about 1 million years or so. And above this mass, we don't see stars having a red supergiant phase. But the good news is if a star has made it to the red supergiant phase and we're seeing it exist as a red supergiant, we can be pretty confident that it's probably not in an interacting binary at the minute. So we don't need to worry about binaries for the red supergiants. Once they're in the red supergiant phase, they're firmly on their path to supernova. So just very basically, the helium core gets exhausted and fuses into carbon, and basically the core fuses heavier and heavier and heavier elements until there's no more nuclear reactions. You have an iron core, and at this point, the star can't support itself against its own gravity, and you end up with a supernova that looks exactly like that. And we see them go off all the time. So in the left-hand image is the Cartwheel galaxy with no supernova, and in the right-hand image, there is a supernova. So I'll give you a second to see if you can spot it. Okay, it's down there. 2021 AFDX. So you can see that this supernova is significantly brighter than the source that was there before. You really can spot them very easily, especially in nearby galaxies. So the type of supernovae that we see strongly depends on the mass loss that goes on prior to supernova. So if a star doesn't have too much mass loss during its main sequence and during its hot phases, it will land in the red supergiant phase, and it will just stay there. It will hold on to its hydrogen envelope, and it will appear as a type 2 supernovae. For stars that are higher mass, they may never have a red supergiant phase because their mass loss rates during the main sequence are so strong. And this will mean that the star never gets over to the cool part of the HR diagram, and you'll see a hydrogen poor type supernovae with no envelope. The star has no envelope at the point of collapse. But we do see red supergiants explode as supernovae. We're in a very exciting time because we can now directly confirm the progenitors to supernovae that we see. So what happens is a supernova goes off, and there's now enough archival imaging, that, especially with HST, that we can look through and try and identify a potential progenitor. This is a particularly nice example because it's been taken in multiple wavebands, so we can see what color the star was before it exploded. You can then wait for the supernova to fade away and go back and say, that star has gone. That was probably the star that exploded. So this is the most direct method we have of linking supernovae to their progenitors. But then in reality, you probably won't have a nice color image like that. You'll probably only have one photometric point. If you're lucky, it'll be a detection. Sometimes it's an upper limit, but you have to make do with that. But what you do is you go through a few steps to convert your pre-explosion photometry into an initial mass to say what kind of star exploded. And there's a lot of assumptions that go into this. You have to assume a distance. You have to assume the extinction around the star. You have to assume what color the star is. And you convert this into, you get your terminal luminosity. And then you have to convert your luminosity at the point of core collapse into an initial mass using a relation like this. This shows a few different initial mass, final luminosity relations from a bunch of models. I can't tell how clear it is on there, but there's quite a range you can get. So for a given initial mass, you would expect a few different luminosities depending on which model you pick. So there are a lot of uncertainties, but hopefully this will get better with things such as the Nancy Grace Roman Space Telescope, which is going to be imaging galaxies in the mid-infrared, which makes this kind of process a little less uncertain. But at the moment, it's very uncertain, but you can do it for a lot of nearby supernovae now. There are a lot of stars where we can get this pre-explosion direct imaging method working. This was done very famously in 2009 by Stephen Smart and collaborators. So this figure just shows the initial mass of the stars, and then on the y-axis, we've just got like all of the stars that have had their progenitors imaged directly. Now, if the progenitor population that was analyzed here followed what we see for stars in the field, you'd expect it to follow this line. So that's basically following the IMF. But what we actually see is this line. we actually don't see any stars exploding in this higher mass range, and we should see them because we do see these stars existing in the field. So it's got people thinking, what is happening to the high mass progenitors? Before I said that we expect to see these stars exploding up to 30 solar masses, and we are just not seeing it. So people started wondering, is the cutoff actually lower, and why is it lower? So one option for what might be going on that's been suggested quite a lot through the years is that actually the red supergiant phase is much more influential on the evolution of these stars than we realize. So in this scenario, a star would have a very quick red supergiant phase, but its mass loss during that phase would be so high that the star would eventually lose its envelope and die as a different type of supernovae. So it would actually leave the red supergiant phase at some point and die as another type of supernovae. And if you look in stellar models, you can see this kind of theory coming about. So these are from the 2000 Geneva models. So in this scenario, a 25 solar mass star is expected to get to the red supergiant phase, and you can see its track ends there. That's where it would die, producing a type 2 supernovae. Above that mass, the stronger mass loss, it doesn't end in the red supergiant phase. So this would put the cutoff for those 2p progenitors somewhere between 25 and 40, which is kind of in line with what I said before. But if we go to a later set of models from this same group, the picture looks a little bit different. So you can see now the 15 solar mass star still ends its life in the red supergiant phase, but a 20 solar mass star actually just has a very fast red supergiant phase and comes out. So this moves the limit for where you would expect to see 2Ps down to 20 from 30 solar masses. Now what's changed between these models? Things get updated in stellar models all the time. There's a whole lot of things you can change and tweak, but quite significantly in these models, the way that mass loss rates were implemented changed very significantly. But it's important to know how mass loss rates are actually implemented in stellar models. So it's not a first principles thing. These models require input from empirical or semi-empirical recipes. And it's basically split into two regions on the HR diagram. So above 10,000 Kelvin, stars are in the hot phase. And in this phase, mass loss rates are fairly well understood. We have a pretty good theoretical model for what's going on. So the prescriptions that are used there are all semi-analytical. Unfortunately, for the cool phase, everything less than 10,000 Kelvin, we don't understand the mass loss rate mechanism at all. There's no theoretical model that can kind of match what we see. So the prescriptions are purely empirical, and they're based off a very small, probably slightly unreliable sample. I'm going to talk more about that later. But also in the Geneva models, they, above 20 solar masses, started to crank the mass loss rates up by a factor of 3, in part maybe to explain this red supergiant problem with their mass loss. So the question is it justified to do this? Are mass loss rates during the red supergiant phase actually higher than what we've been assuming for a long time? So there are a lot of empirical prescriptions to choose from when you're trying to pick your favorite recipe to go into your stellar models. So you can see that a given luminosity, depending on which relation you pick, you can end up with a very significantly different mass loss rate at that point. But the one that's most commonly used is the one that I've highlighted in green. It's the Diaga prescription from 1988. But even within that one prescription, there is a scatter about plus minus a factor of 10. And just to put that into context, that could be the difference between a star losing all of its envelope during the red supergiant phase or losing absolutely none of it at all. So it's really not well constrained. So I think it's fair to say that it probably needs a little bit of an update, but where did this prescription come from? It was actually more of a literature study. So the authors went and collected every single mass loss rate luminosity measurement that was available in the literature and put it all together and derived a relation for mass loss rate from it. That includes hot stars. It's actually no longer used for hot stars. The sample is highly heterogeneous because it was just whatever was available in the literature. There were no controls for initial mass. There was no control for metallicity. There was no control for the method used to calculate mass loss rate. And for the red supergiant phase, it actually only includes a handful of red supergiants, mostly the famous ones that are kind of nearby, like Betelgeuse or BYCMA. Anything that was really bright and easy to image in like the 60s, 70s, and 80s is probably in this prescription. But a lot of these stars have had their luminosities significantly adjusted since then because we have better distances, we have better ways of determining luminosity, but they're still in the prescription that are used basically in all stellar models today. But there is a way that you can do it better. You can look at red supergiants in clusters rather than relying on a sample of galactic stars. And the reason red clusters are so useful is that you can kind of make some assumptions that are very helpful for putting constraints on what you're looking for. So if you're looking at a cluster, you can probably assume that all of the red supergiants have the same metallicity. You can kind of assume that the population is coeval. So this would mean that every red supergiant you see is probably the same mass to within about 1 solar mass, and that's because the red supergiant phase is so short. So you kind of when you're looking at a cluster, you're kind of looking at a population of stars that are all the same initial mass. And if they're in a cluster, they probably have a better constrained distance. You're going to get much better distances to stars in a cluster than you are to stars in the field. So how do we measure mass loss rates? So red supergiants emit their light, and it gets absorbed by this dust layer and scattered out. And you can model the mass loss by modeling the mid-infrared excess of the star. So this is what it looks like in a little cartoon form. So the light is absorbed in the optical from here, and then it's re-emitted in the mid-infrared. At around 10 microns, you'll see this really significant bump. That's what it looks like with real data. So we fit models to the photometry that we have and determine a mass loss rate. We make some assumptions, and some assumptions using a radiative transfer code. In this case, I use one called DWST, and you can derive a mass loss rate for each red supergiant in a cluster. We can also work out their luminosities based on their photometry, and then we can end up with a new mass loss rate luminosity prescription. So that's what I did. For every red supergiant in all of those clusters, I derived each of their luminosities and each of their mass loss rates, and this is what we see. So we've got luminosity along the bottom, and we've got mass loss rate along the Y. So each different color symbol is a different cluster. And what we found, though, is quite interesting, is that while the gradient of the relation in each cluster was pretty much the same, the offset was quite different, and it actually goes with initial mass. So the stars in RSGC1 are more massive than the stars in the 3 other clusters. So I think these were about 20 solar masses, when these are all like between 10 and 12. So you see this, so from this we were able to derive an initial mass-dependent mass loss rate prescription. And by taking the uncertainty out of the mass, we were able to reduce the scatter on the relation. So this just shows some residuals. So this is our prescription on the left. You can see that the scatter is about 0.3. It's much lower than Diaga, which is about 0.5. But perhaps most significantly, what we see when we look at these residuals, so that's just comparing the real individual mass loss rate measured for each star compared to what the prescription predicts. The Diaga prescription massively over-predicts mass loss rate for the most massive stars. And that's really important because these are the ones whose fates are the most uncertain. So, you know, it might not look so bad at the lower masses, but for the more massive stars, it's massive. Even without this factor of 3 cranking up of the mass loss rate, it's already doing an overestimate by quite a significant factor for the most massive stars. So if we compare what we see or we expect to see for a massive star during the red supergiant phase, how much mass it would lose, if we compare that to what the Geneva models predict, this is what it looks like. So for a 20 solar mass star, the Geneva models from 2012 predict a star will lose around 10 solar masses of material, and that is what's forcing the star to move back to the blue and to leave the red supergiant phase. What we find is that actually a 20 solar mass star probably loses less than 1 solar mass of material, so absolutely nowhere near enough to make any difference to its evolutionary path from that point. So there's no evidence for enhanced mass loss, certainly, there's no evidence for this enhanced mass loss, this increasing of a factor of 3 to explain the red supergiant problem. And what that means is that mass loss rates cannot explain this missing set of high mass progenitors. So we've done a lot of work on this. We've even looked at short enhanced mass loss rate phases that may be like shorter than these kind of quiescent mass loss rates. We don't see any evidence for it there as well. I don't have time to talk about it right now, but you can feel free to ask me about it. But the bottom line is that mass loss rates during the red supergiant phase are really insignificant. They make almost no difference to the evolution of the star. So mass loss isn't the answer to the red supergiant problem. So where are these missing high mass progenitors? And this has some people have suggested that the lack of high mass supernova progenitors is actually telling us something about where we should expect to see black holes start to form. So the path I told you before for stars between 8 to 30 solar masses is that they'll have their supernovae and leave behind a neutron star remnant. But what if the upper limit to this is actually a bit lower? What if at some mass you don't see any explosion at all, the star just collapses straight to a black hole without any noticeable signature? this is called the direct collapse scenario, or a failed supernovae. And it's something that has picked up a bit of traction amongst theorists in particular. So this figure again just shows the red supergiant masses from that direct imaging. And then this group ran models across a range of masses, and they looked at the core structure of each star and determined whether or not that star would be likely to explode or implode based on how compact the core is. So this kind of like chocolatey bar thing down here, everything that's black is a star that would end with an implosion, and everything that's green would end with an explosion. So you can see that above this mass, stars are less likely to explode. You have these islands of explodability, but it's not. They don't predict that most of these stars will explode. That's a big question. It's because they have to like tweak the models. They run them at like 0.1 resolution, and they have to tweak a lot of models to get them to the end. So some of them are a bit noisy, but the kind of explosion implosion blocks are probably okay. Mm-hmm.
How do they know whether it explodes or not, given that they've only barely been able to sort out some of the neutrino?
Yeah, I mean, so they just look at this parameter called the core compactness and just try and, there's like a cutoff above which they say this would implode or explode.
But I thought that now
yeah, this came up very recently at a conference I was at, so what they need to do is rerun the models, but they're not doing it yet. But this is where the theory is at the minute, so just don't worry about that. But the exciting thing is we've maybe seen one direct collapse event already, and it kind of neatly lands right here in one of the islands of inexplodability, in one of the implosion zones. It's called N6946BH1. So it was, so that is the first candidate. So what we know about this star is that prior to its disappearance, it had a luminosity of around 5.5, which would make it a red supergiant of around 25 solar masses. It had a very moderate outburst, and then it disappeared. So this is HST imaging of the source on the left. So in 2007, it was pretty bright, pretty noticeable. But there's a team that are scanning the sky, looking for things that disappear. And eventually they went back, and they found that it had completely vanished in the HST filters. So this is obviously very exciting. It's the first candidate. But has it really disappeared? Like, what else could it be? The star could just be hiding behind a layer of dust. We do see red supergiants have random, very, very short outbursts that can shield the star from view. So I showed you that figure before where the flux in the optical was kind of cut out and then re-emitted. If there was enough stuff in the way, even temporarily, you can imagine it would force the star to be almost invisible in the optical. Betelgeuse had a great dimming. Maybe that was to do with dust. There's also a star in galaxy M51, which appeared to disappear for, I think, about 3 years, and then it reappeared later. It's called DS1, Dusty Star 1. So the only way to answer this, though, to see if the star is really still there, is to use JWST. And I was very fortunate to have a Cycle 2 proposal accepted. We went back and we looked at BH1. And what we found was that there is indeed still a source at the site of BH1 across NIRCam and MIRI filters. So we looked at from about 1 micron all the way up to 21 microns. And you can see that the source is particularly bright in the MIRI filters. So some of these filters kind of match what the HST filters had already seen. So it is much fainter in those, but there is a very bright source in the mid-infrared. But how do we interpret this? The luminosity of the source comes out to be around a log L of 4.7, which is between 30 and 25% of the progenitor luminosity. So it is significantly fainter. And you would maybe expect that if the star had like a spherical outburst, that all of the light would have been recovered in the mid-infrared. But what we see is that the source is actually much, much fainter. So is it a failed supernova? Have we actually seen a star collapse to form a supernovae? Does it make sense? Well, the problem with this kind of theory is that the models of failed supernovae aren't really tight enough to make any useful predictions that we can actually go and test. So a paper by Lovegrove and Woosley suggests that any outburst from a failed supernovae, you would expect to see a little outburst, should last around 500 days. This one was much shorter. I think it was about 100 days. Another paper says that if there was to be a failed supernova, you would see some lingering infrared flux. It could last anywhere from a few minutes or to a few thousand years. So that's not very constraining. There's also the fact that there's no X-rays detected. You can imagine if a star had collapsed and left its envelope behind and formed a black hole in the middle of that, you'd maybe expect to see some sort of accretion, some sort of X-ray signature, but there is absolutely none, like nothing at all. And some authors say that maybe this is to do with some kind of weird shielding effect, but they do not detect any X-rays at all. Another recent paper came out that looked at, well, how bright would a failed supernova look? Like, you can't just blink out of existence without any kind of outburst at all. And what they say is that for a star like BH1, if it was a 25 solar mass red supergiant, you'd expect to see something much brighter. This figure is a little confusing, but basically this star here shows how bright you would expect a red supergiant that was 16.5 solar masses to appear in like a very small outburst. So it's much fainter than a supernova, but it is a noticeable outburst. And BH1 is actually way fainter than that. Its outburst was significantly fainter. So maybe it doesn't make sense with that as well. Another option is that maybe there was a stellar merger. I've already mentioned to you that massive stars exist in binaries and multiple systems, and that these can have a huge effect on the lives of massive stars. And a lot of non-terminal, lowish luminosity transients are associated with binary interaction. So there's things called intermediate luminosity optical transients, which is a very descriptive name, luminous red novae, luminous blue variable eruptions. All of these things are kind of thought to come from binary interaction. And if there was a merger of two stars, you can imagine that it would be a very, very messy interaction. If they completely merged, you would probably see an outburst, and it would result in a very highly asymmetric dust shell, so it wouldn't be nice and spherical. It would be really messy. And we might only end up seeing 10 to 20% of the light, depending on what viewing angle you're seeing all of this dust at. So this here is Eta Carina, which is a luminous blue variable star, and this is at least a binary, if not a triple system, but it had a very messy merger event, had a little outburst. It had quite a big outburst in the 1800s, and it still looks a mess now. It's still really dusty. There's a lot going on there. And actually, if you look at the light curve for BH1, it kind of also makes sense with this. So this is just the light curve pre and during the outburst and following the outburst. So the solid green, red, and blue lines are the BVR filters. The grey lines are kind of the mid-infrared, the Spitzer photometry. So you can see in pink where the outburst was. It didn't last very long. But interestingly, prior to the outburst, what you can see is this phase where the star appears to get redder. So you can see that the mid-infrared fluxes, the near-infrared fluxes are getting brighter, implying the star's getting redder. This could be, two stars spiraling around each other, tearing off loads of material, creating loads of dust, creating loads of mess. And actually, before the reddening phase, it didn't even look like a red supergiant at all. It actually looked like a yellow supergiant star. So if you go back a few years, it didn't even look like a red supergiant. And it looks very similar to a merger event that we have seen, and we know was a merger because we could tell the two stars were going around each other from the light curve. This is V1309. So you can see prior to its outburst, it was getting brighter, and then it had its outburst, and then it's faded away. But we know that was a merger. This kind of phase where it's getting brighter was termed the death spiral. So it could be that what we've seen for BH1 is two stars in spiraling on each other, creating a load of mess, outburst, and then it's faded away. So we also may not have been seeing the progenitor to BH1 in its quiescent state. It could have been getting brighter prior to this outburst. We just don't know. So where to go with that? We just have to kind of keep following. We've asked for more JWST time. We could also do some in-depth radiative transfer modeling to put meaningful limits on any potential surviving star. A lot of radiative transfer codes are 1D, but there are kind of 2D and 3D codes available that we could look at. So I guess the moral of the story for BH1 is that don't name stuff until you know for sure what it is. But hopefully we will get more time with JWST to go back and keep monitoring the star and see how the source changes. Okay, so is there another way to search for this threshold for black hole formation? Is there another way to test this idea that actually what we're seeing is the cutoff for where these events should start to form? So we can learn a lot from supernovae and their light curves. So this figure on the left is the light curve of the light curves of a bunch of type 2 supernovae. So you can see that type 2Ps, which is the type that red supergiants explode as, have this kind of plateau phase. It lasts on the order of like 100 days. And the length of the plateau is really closely tied to the envelope mass at the time of collapse. You can also take spectra of your supernovae, and you can see if there is any evidence for interaction between the star as it's exploding and any material that is sat around the star. So it can tell you a lot using the light curves and the spectra. And we are about to get a lot more data from Rubin-LSST. We're going to get a lot of light curves. We're going to be detecting supernovae like we never have before. But the important thing that we need is models that are, useful, and we'll be able to apply to all of the data to really understand what's going on with these supernovae. So we put our new prescription into the Stellar Evolutionary Code MESA to see what effect these lower mass loss rates would have on the appearance of a star as it approaches core collapse. So this figure just shows the initial mass of the star against the final mass. We ran models between 12 to 27 solar masses, and the only thing we changed in these models was the mass loss rate prescription. So the prescription that was in there was just the standard Diaga prescription without this factor of 3 cranking up. And you can see the new prescription, there is a positive correlation between the initial and the final mass, whereas the old prescription kind of predicts this plateau. If you look at the hydrogen envelope at core collapse, which, as I said, is important for the length of the supernova plateau, we see that, again, there's a positive correlation between the hydrogen envelope mass at core collapse and the initial mass of the star from our models, whereas the models that are using the Diaga prescription, basically you're getting almost the same hydrogen envelope mass at core collapse no matter what initial mass you put in. So since almost all models of supernovae use this old prescription, and I do mean that they basically all use it, we actually have no idea what a light curve from a high mass progenitor would really look like. It's also true for when people run spectral modeling of supernovae, they all use these old prescriptions, which are overdoing the mass loss rate, in particular for the high mass stars. So what I'm hoping to do is to use these new models and a supernova explosion code. There's one called SNEC, there's another one embedded into MESA called Stellar, which you can use. And I want to create a new suite of models of supernova light curves that can be directly tested with data from Rubin-LSST. And this is a great project for this because with Rubin, we'll end up with a lot of light curves and not a lot of spectra. So this is the kind of ideal project for that. So we'll be able to make testable predictions. For example, will we be able to detect high mass progenitors with LSST? If we're not going to be able to detect them, why are we not going to be able to detect them? What else is going on that's kind of stopping us from seeing? What would these explosions look like? And if we should see them and we don't see them, why? Is it that we are actually seeing the threshold for black hole formation? Is this the lower limit of where that starts? What else could hide a high mass progenitor? Again, there's binaries, there's all sorts going on. There's a lot of things that we will be able to tie down using things like population synthesis and these models. There's also things that we can learn about stellar evolution from gravitational wave surveys. So a lot of people have been predicting what kind of black hole masses we should be seeing with the LIGO Virgo project. And basically, all of the theoretical models of these things predict that there should be some sort of mass gap where we should see no black holes at all forming between about 50 to 120 solar masses. And this is predicted across basically all of the models. But unfortunately, well, not unfortunately, we keep finding black holes in this mass gap. So there was a 6870 solar mass black hole detected in a binary system. This was before LIGO Virgo. We also keep finding binary black holes within the mass gap. So in this case, both of the stars that coalesced to form one black hole, they were both in the mass gap. And it's really difficult to explain that when so many theoretical models predict we should not see anything there at all. A few things have been put forward. So some papers have arbitrarily fiddled about with the mass loss rates, just turning them right down to nothing. And if you do that, then you can move the position of the mass gap. But again, this was just kind of ad hoc done, like what happens if we turn the mass loss rates down. Other papers, such as this one, to kind of solve this problem, they force the stars to stay in the hot region of the HR diagram where the mass loss rates were a bit lower, and that also stopped the stars, stopped this mass gap from forming, or moved the position of the mass gap higher. There's been other theories, including multiple merger scenarios. So maybe the stars have already undergone merging, but you would need 2 sets of mergers to then merge again. It maybe is a little contrived. Some people have suggested some sort of modified gravity theory, which is, again, one of the more exotic takes. So people are trying to figure out how we're seeing stars there. What do all of these mass gap predictions have in common? It's the Diaga prescription again. So the cool supergiant phase is everything less than 10,000 Kelvin, but there are actually 2 distinct phases there, really. There's the red supergiant phase, which I've already told you about, and there's also the yellow supergiant phase, which is more of a transitional phase as stars are on their way to the red supergiants. So this phase is really quick, like 10 to the 5 years, but the Diaga prescription has quite an influence here as well. So for yellow supergiants, the situation for mass loss rate is arguably even worse than for red supergiants. For one, the prescription is only made up of, I've put 8 objects here, but I counted it's actually only 6 objects that are usable. So there's only 6 yellow supergiants in there. In the figure on the right, I show the positions of the yellow supergiants that are used in the Diaga prescription. So the black lines are ones which have had their luminosities revised. So this one here, you can see its luminosity dropped very significantly from 5.5 to 3.5. It's because it's not a yellow supergiant, it's actually a planetary nebula, but it is still in the prescription that is used very widely. So actually only like 3 of the stars that are in the Diaga prescription have high luminosities. And they don't actually have mass loss rates that are particularly high. The problem is that this prescription is extrapolated far beyond the region to which it was calibrated. So we end up seeing stars that are really high mass doing really crazy things in stellar models that is probably not realistic at all. So if you look at the red line here, this is a 100 solar mass star in a parsec model, and you can see that through that very, very, very short yellow supergiant phase, it somehow has 30 solar masses of material ripped off because of the extrapolation of this prescription. And it actually ends up hitting mass loss rates of a log m of like minus 3.3. That is far, far, far higher than anything we've ever seen for any yellow supergiant or red supergiant. It's not anything that's been observed, but these models all have it in. And it's particularly bad for the higher mass stars because it is so extrapolated. And all of these mass gap predictions have this physics within them. Oops, sorry, there's the 3.3. So it's just way higher. You can see the green line actually hits an even higher number, but I didn't highlight it because that one it's too high. It seemed silly to me. But I think what's obvious is that yellow supergiant mass loss rates probably also need to be reappraised and to have their mass loss rates looked at again. The problem is it's not quite as simple as for red supergiants because they don't produce as much dust, so you can't do the simple mid-infrared fitting that I was doing for the red supergiants. What we actually need to do is use stellar atmosphere models and strap a wind on and see what effect a wind would have on a spectra. But we need a good sample of yellow supergiants to do this. And luckily, M31 has been imaged extensively by the FAT survey, and there are a number of yellow supergiant candidates within there that we've identified with colors. And then I've been able to get spectra for each of those candidates, which will at some point allow me to confirm whether or not those are yellow supergiants, and they will be the basis for the observational set I'll use to test new stellar models on. So I'm going to build new atmosphere models and strap winds on of different strengths and see if we can derive a new yellow supergiant mass loss rate prescription, and this can then be input back into stellar models. And what I suspect will happen is that what we'll see is that mass loss rates during the yellow supergiant phase are low. You don't need to ad hoc fiddle numbers to make it work. They just actually are really low. And this may reduce the tension between observation and theory for yellow supergiant, for the black hole mass gap, because I expect the mass gap could move up. So uncertain mass loss rates really do affect higher mass stars as well. Okay, so there is also a lot more that we can learn from red supergiants, yellow supergiants in stellar populations. And I don't have time to go into like a lot of detail with this, but I just want to stress some results that are really can only come about when you look at stars in population rather than looking at single stars. So for one, if you look at the luminosity function of red supergiants, you can determine something called the HD limit, which basically means the maximum allowable luminosity for a red supergiant. And this is something that is very useful and interesting because it can give you another handle on where you should expect red supergiants to form, where you shouldn't expect them to form, how long they survive at certain luminosities. Again, you can learn about the mass loss rate from this. So I've done some work on that. You can also look for evidence of binaries using red supergiant populations. So to get the initial masses for those red supergiants I showed you before for the mass loss rate prescription, I had to find a way of determining the age of the cluster that was independent of the binary fraction, because binaries can rejuvenate things, make things look a lot younger than they really are. So we were able to come up with a new method of aging young massive clusters that is independent of the binary fraction. And to do that, you just use the cool supergiant population. It gives you a really good handle on the age, because in the main sequence, stars are rejuvenated and the cluster looks younger. It's also using populations that we can look at things, weird clusters such as Western 1. So Western 1 is a very famous cluster because it has a whole host of massive stars within it that you probably wouldn't expect to see together if you were just reliant on single star evolution. So there are luminous blue variables, there's red supergiants, there's yellow supergiants, there's a ton of Wolf-Rayet stars, there's a magnetar, and basically the crossover period for when these stars can all coexist together according to like single star theory is really small. It would have to be like a 5 megayear cluster, which would make some of these stars some of the most massive known in the universe, and it would also make the Western one of the most massive clusters known. But when you actually look at the population and you look at the cool supergiants within there, what you find is that the population of cool supergiants is significantly older than all of these hot stars would imply. So it could be that because of the high binary fraction causing the cluster to look younger, even though it's actually older, or it could be that we're looking at two populations in front of each other. But this is important because Western 1 was always considered to be like kind of like a Rosetta Stone cluster. A lot of people calibrate, like kind of intrinsic colors of clusters using this kind of cluster, assuming it's one age, this is what color we should see from the integrated light. But in reality, it's actually probably not the most massive cluster. It's not a starburst cluster. And the only way we can figure that out is using stellar populations. But this kind of work is focused on nearby clusters and galaxies because Spitzer, Sophia had pretty low spatial resolution, so it's been really difficult for a long time to push to further distances. But of course, we're now in the age of JWST and extremely large telescopes, so this type of work we will be able to push much further out. We'll be able to probe many more metallicities. We'll be able to learn a lot more from stellar populations than we can at the minute. There's already great archival resources that can be used. So there's the Legis survey, which was an HST survey looking at young clusters across a range of metallicities. There's also the FANGS HST and JWST survey, and there's going to be an absolute ton of stellar clusters in there. And again, it's probing distances and metallicities that we just cannot access at the minute. So there's lots of work to be done. So the takeaway from that is that there's still a lot more to learn from massive stellar populations. Okay, so I'm just going to reiterate that stellar evolution is hugely important. It is one of the oldest subfields in astronomy. It's been going for a long time. But all of these modern surveys, all of these new computational tools are revealing that there's loads of things that we actually don't have a very good handle on. And this does have a ricochet effect on a lot of areas of astronomy. So for example, if the threshold for black hole production is lower, we'd expect to see a higher binary black hole rate. For simulations of galactic evolution, they need to know the supernova rate. And if the supernova rate is actually lower, if these stars do collapse, this could have a huge knock-on effect for their predictions of metallicity and things like that. And also, any of the predictions that are made in stellar physics, so for example, what kind of mass range do we expect for black holes? Do we expect stars to implode or explode? Everything that is predicted by these kind of papers is highly dependent on the assumptions made during the cool supergiant phase. So I hope that I've convinced you through this talk that it's vital that we understand stellar evolution and that the endpoints of massive stellar evolution are understood. So I will wrap up there and say thank you.
for a great talk, Emma. Questions? Shannon, of course, you're.
Hi, Shannon Curry. Great talk. So you talked in your Dusty model about that 10 micron shoulder.
Mm-hmm.
Does that always appear, and whether it does or does not, could anything dampen it? Are there other what are the physics where you would not see that 10 micron sort of signature?
Yeah, that's a great question. So that particular shaped feature is indicative of silicate dust, which is what we expect to see around red supergiants. It's stronger if there's more dust there, but it can be dampened if the cluster is like highly extincted. So RSGC1 is one of the clusters I looked at, and it's in like a very dusty region of the galaxy, and you have to kind of figure out what the base level extinction for that cluster is and then like subtract it off so you can see it. In terms of physics that would shield it, sometimes very rarely things can be so dusty it can almost invert it, but that would have to be quite far out to do that. It's quite rare. Oh yeah. So if it's more dusty, it'll have a much more pronounced bump. If it's less dusty, it's almost flat.
Hi, thank you for a really great talk.
Mm-hmm.
It's great.
So if for the red supergiants, the clusters that I looked at, they were either LMC, metal-LSST, or galactic, and we didn't see like a significant shift. This is something that needs looking into. It's kind of assume that lower metal-LSST if it's an extremely low metal-LSST, the mass loss rate will be lower, but it's kind of at the moment up in the air, like over what range that would have like a really significant effect. And I think that's something that using like fangs and stuff will be really good for, because we'll be able to push to like different metal-LSSTs and really see like the effect it actually has on red supergiants.
Thank you.
Mm-hmm.
Was what actually happened. Do you expect that that's still something that would be common?
The direct collapse?
Yeah.
I think it's not common at all, but people would disagree with me on that.
Okay.
I think that actually it's the kind of thing where there's not really any good theoretical, like the theory that is there, like some of the models need to be updated. Like a lot of these implosion explosion plots use, again, these mass loss rates that are wrong. They have to like really, really tweak their models to the very end to get them to not crash. And I think it's something that needs to be looked at more. I think if there were direct collapse supernovae, you'd probably see an outburst. So either we are already seeing them, but we just don't know what they look like we're just interpreting, lower luminosity transients as something else when really they are, or we're not seeing any of them at all. But I think what we need is better predictions for what it would look like so we can start to understand.
Okay, thank you.
Who's got questions there? I have one too, but I'll let other people go first.
Hi, that was an awesome talk. Thank you. You laid out really convincing evidence for why there's massive and important uncertainties in how mass loss rate affects things we care about with red supergiants. For other kinds of stars that I know a little bit more about, I know people care a lot about uncertainties in angular momentum transport, in overshoot, in chemical mixing.
Mm-hmm.
I don't know a lot about red supergiants. I guess I was wondering, do these other things also matter a whole lot here, or is it really like mass loss rate is the number one thing that the only thing that we're worried about for these stars for constraining these issues?
Yeah, that's a really good question. I think that the mass loss rates are a good one to look at because we can measure it and then put it back into models and see really what effect it has. A lot of the time with things like overshooting or mixing, people would just kind of fiddle the numbers around, or like a lot of it is calibrated off the sun, which might not be very reliable. So it's just at the minute difficult to think of a better way to do that. So you kind of just have to make some assumptions, and papers come out all the time that just move overshooting about, and then they can change where stars end, and blah, blah, blah. But there's not really very convincing evidence for like why you should do that or justification for doing that at the minute. Whereas the mass loss rates we can measure, we can put them back in, and we can see what effect it has.
Okay, I have a question for you. What would be your first thesis project for a CU PhD student?
Ooh, that's a good one. I think doing the yellow supergiant stuff is probably the most well-rounded, like long-term project that is kind of good to go now. I've got the data ready for them. I've got the tools ready to like help them set up these atmosphere models, and that's something that kind of like no one's done for a long time. There's not really any atmosphere models for yellow supergiants. They'd really be fit in a niche, which is interesting for the yellow supergiants themselves, but then the consequences of all that work are going to be super important for LIGO, Virgo, and predictions like that. So I think that would be the one I'd be most excited to like get a student going with.
Awesome. Watch out, students. It's mine. Yeah.
Is it okay? Cool. Thank you. It was a great talk. Really, really cool. So apologies if this is just a completely naive question that's totally unrelated, but I'm curious how this might impact our understanding of POP3 stars, and in particular the remnants, and potentially things like feedback models in in say fire, which is a cosmological simulations of stellar feedback in the early universe.
I hate when people say it's a naive question. It's always the hardest question. Yeah, I mean, the mass loss rates in the early universe were probably much lower because it was much, much lower metallicity. You could get stars that were much more massive. So I don't know is the answer to that. Mass loss rates would have been almost non-existent, really. You're just waiting for things to die.
Weird in the early universe. Yeah, that's a yeah.
Thank you. Great talk.
I was wondering if you study mass loss a lot. Physical mechanism for mass loss. I'm interested in any sort of like anisotropy during mass loss, and like kicks on the central object, like to the remnant when mass loss happens.
Yeah, great question. The answer is that we just really do not know what's driving red supergiant mass loss, like, at all. The thing is that you've got your red supergiant, and then you've got like a big cavity before the dust layer, and we don't have any model that can really explain how to accelerate dust all the way up there. It's probably a combination of things like radiation pressure and pulsations, but mass loss from red supergiants is not constant. It ebbs and flows. There'll be phases where it's stronger and phases where it's weaker. It's really, we always model it as spherically symmetric because over the lifetime it basically is, but it's actually an inherently non-spherical process. It's actually very clumpy, very random, very outbursty. We just don't know what's driving it at all.
Thank you.
Man, you guys are really making me cruise. Oh, is there someone over here? Oh, yeah, I'm staying over here.
Hi. You were talking about one of the difficulties with this study with understanding where this black hole threshold is. You were talking about the mass gap and how we find so many of these black holes in that gap.
Yep.
Could you just clarify why can't you find the mass, or why can't you find the black holes in this gap? Like, what even is this gap?
The mass gap?
Yeah.
You mean from the theoretical side?
Yeah.
Yeah, so it's to do with the amount of envelope that stars hold onto in this mass range affects whether or not they die as something called like a pair instability supernova, which basically means the star completely destroys itself when it explodes. So there's no remnant because it's been destroyed.
Mm-hmm.
And whether or not stars would end up like that turns out to be super dependent on the mass loss rates.
Got it.
Yeah, so that's
okay. Thank you.
Did we have a question over there somewhere? Oh, nice. Same thoughts. Okay. Any other questions? Great. Oh, Steve. Okay. You were almost off the hook.
So you made a good case why the old de Jager mass loss rates were bad for the massive stars. Do people still use them for the lower mass stars, like AGB stars and things like that? Or
Well, I don't think so. AGB stars are a little bit different because they are dust-driven winds that you can explain their winds just like the radiation pressure on the dust. So they've got a different mechanism. I actually don't know what prescription they use for modeling them. There's also a prescription called the Van Loon prescription, which was based off like a set of AGBs and a couple of.
there's still a lot with an order of magnitude of slop in them.
It's super uncertain. Yeah, but we at least have a better idea of what's driving the mass loss there.
Great. Let's thank Emma again.